ladies and gentlemen, class recording has begun. So, on Wednesday of this week, we discussed the introduction to acceleration. And we said that in chapter 2, in unit 2, we introduced motion. And we talked about describing motion, and we talked about how we define those things and how we, how we represent all those things about motion. But all the motion that we talked about in Unit 2 was all constant velocity. Something was either moving or it wasn't moving, and if it was moving at a constant rate. The amount of distance it went each time was the same the whole time. But that's not the real world. Things change what they're doing all the time, and so that's what acceleration is about. And we talked about that defining acceleration. Acceleration measures the rate of change of an object's velocity. So in order to calculate the acceleration, you need to know how much does the velocity change, right, delta v, over the time frame during which that acceleration occurs, or that change occurs. Because acceleration tells us how much velocity changes each second. That's what acceleration does for us. Okay? Good there. Okay with those concepts, at least initially? All right. Starting off today, if you would please, open up your book to page 81. Page 81. So on page 81 is, at the bottom, is the 3.1 lesson check. So that's just the chapter, the section review for section 3.1, which is the introduction to acceleration. And on the 3.1 lesson check is question number 11. So it says, can an object accelerate even if its speed is constant? And the answer to that question is yes. Because we talked about that acceleration being defined as the change in velocity over time can look three ways, right? What can be acceleration? What counts as acceleration? So, well, in this case, turning, right? But the two that we think of most often, right? Speeding up, slowing down, right? Those two things would definitely count because those are definitely changes in velocity, but changing directions is also a change in velocity because velocity is a vector quantity. It has both magnitude and direction. So even if you're going a constant speed, if you turn and go a different direction, that is a new velocity. So that counts as acceleration. Good there, at least conceptually to begin with. Okay. Next, turn to page 76, if you would, please. Turn to page 76. On page 76, up at the top, there is a section called Practice Problems. And in those practice problems, there's some pretty straightforward calculations using the formula for acceleration. So, just to review, and if I had my little magic pen and it was working properly, I would write this on the board. So if you were watching this video, you would actually get to see it, but because mine isn't, got to go old school. Okay? So we talked about that acceleration is defined as change in velocity over change in time. Okay? But we've discussed that the delta notation, right, the change, in order to figure out the change in something, you have to know what? Initial and final, right? So we can modify that equation to look like that, right? Where the top of the fraction is v final minus v initial, and that represents delta v. Good there? So with that being said, on page 76, numbers 2 and 3, let's use this formula for acceleration, and let's calculate or do these two problems, right? I'll kind of do them slowly up here on the board so you can kind of check and see how you're doing. And then we'll come back and discuss. Okay? So number 2 and number 3 on page 76. So for number 2, that's your relevant information, right? That's the information first that we're looking for, and then second that they gave you in the problem to work with. And then manipulating that equation, right, to get what we were solving for by itself, it would look like that, which is written on the board and not on the screen. Then for number 3, there's all your relevant information. Even though it doesn't specifically say so in the problem, we can assume that the chameleon's tongue was going at 0 meters per second before he started moving it. All right. Good there? Didn't sound very convincing.
No, I was okay.
All right. Questions about those two? Okay. Next, let's flip to page 79. Let's flip to page 79, please. On page 79, down at the bottom, is the practice problem number 7. Practice problem number 7. So it says, the velocity time graphs of 4 cars are shown in figure 3.8. Part A says, which of the 4 lines indicate a car that's slowing down? Part B says, which of the 4 lines indicate a car that is speeding up? This deals with our graph of velocity versus time. In lab on Wednesday, you got introduced to the velocity time graphs a little bit and analyzing those velocity time graphs and taking a look at what's going on at a particular moment in time. Now, these are different from the position time graphs that we introduced in the previous unit, right? What does a position time graph tell you? What can we find out? Julie, go ahead. Where it is in relation to the reference point at any given moment in time, okay? But this velocity versus time graph tells you what instead? What does a velocity time graph versus time graph tell you? It could, although indirectly, what was saying over there? How fast it's going, but also which direction it's going. So whereas a position time graph tells us where, a velocity time graph tells us what. It tells us what an object is doing. We can't really tell anything about individual positions from this graph. We can talk relative terms, but we don't know exactly where all these things are happening. So with that in mind, let's take about 30 seconds and let's talk about these 2 questions, okay? Because these ones need a little verbal reinforcement, okay? So, in your small little 2-3 person groups, let's talk about which of the 4 lines represent something speeding up, which one's slowing down. Go. Okay, that's good. All right. All right, so on this graph, there are 3 pictures. There are 3 lines that represent a slowing down effect. And that's lines number 1, number 2, and number 4. Okay? And then for B, there's only 1 line that represents a speeding up, and that's number 3. Okay? So, to properly analyze this, let's talk. This line right here, okay? That line that I just highlighted. On this graph, what does that line represent? 0 what? Well, sorry. If a graph shows up on that line, what is that saying about its motion? It is not moving because the y-axis on this graph represents velocity. And so if something is on the x-axis, what's the y value of that graph at that point? 0. And if something is at 0 velocity, that means that it's not moving. Okay? But in terms of these graphs, okay, so that means that lines that are moving towards the x-axis are doing what? Slowing down. if we took a look at, let's say, this spot right here, this spot right here, this spot right here, and this spot right here on graph number 1. If we looked at the y values of those ordered pairs, what would we see about the y values of those ordered pairs that I just put on that graph? They're all above 0, meaning what, Maxie? That means that, what does that tell you about the motion? You're still moving, and you're still moving in a positive direction, okay? But what's happening to the number there? They're getting smaller, right? So you're still moving forward, but slower, 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 okay? But on this graph, here, 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 and here, right? If we looked at the y values of those 4 points, what would we see about those? First, they're all what? They're all negative, meaning, Logan, what? Opposite direction of what red's going, right? Okay? What else then? If we started looking at their numbers, what would we see about their numbers, Anthony? Say again? They're getting bigger if we think about it in terms of a number line, right? They're going from, like, let's say, -4 to -3 to -2 to -1. But in this graph, the negative or positive doesn't tell us anything about how big something is, right? It only tells us what? No. The positive and negative only tells us the direction. So what could you tell me about this spot here and this spot here? How fast are they going? They're going the same speed, but different direction. Okay? So even though this graph tilts upward, right? Even though this graph tilts upward, it keeps getting closer and closer and closer to what?
0.
To 0. So that means it's doing what? Slowing down. Is that okay?
Yeah.
All right. This might take a little bit longer than it normally would, but I'm going to do this, okay? Here we go. If I had my pen, this would go super fast, but I don't, so. All right. What? Well, I have it. It just doesn't work. Yeah. Mine doesn't work at all. Like, it doesn't turn on, so. Got a battery in it. So. Okay. So here's an intersection. Here's an intersection. And there are 3 cars approaching this intersection. First, a red car. Second, a blue car. Third, I'm not going to use green because those graphs are green. I'm going to go orange. Okay. Third, an orange car. Okay? So, red. Moving this way. Orange. Moving that way as well. But, okay, not as fast, right? As you can tell by the whoosh lines. Okay? I will refer to those as such from this point forward, whoosh lines. Yeah. And then blue. He is, yes. Although I didn't make my road quite wide enough, so here, let's do this. Actually, here, let's do this. Like I said, yeah, that doesn't that Knowing that it's just that easy to fix a road like that, doesn't it make it really seem ridiculous how long that parking lot is taking? So, don't know what's going on there, but maybe. All right. So, now, at this point right here, no, this point, okay, there is a stoplight. There.
It's actually pretty good.
There. And I'm pretty sure that's, yeah. There we go. Okay. All right. So, I know. That's what I'm going to do this in a second. Okay. So, these cars are driving along the road. And this stoplight turns yellow. Okay? All three of these drivers decide that, no. All three of those drivers decide that they are not going to make it through this yellow light. So as safe drivers, which you all should be as well, they decide to stop. Okay? The motion of these cars is represented by three of the lines on that graph. So my job for you is to discuss amongst yourselves in your little small person groups which number line goes along with which car. 1 minute, discuss, go.
Wait, okay, this is easy. So, those have two lines that are not and there's two sides of one. Oh, makes it easier to know which one to use. Oh, because there are directions there. Okay, so red is positive, negative. Blue is a negative. Yeah, it's the only one. Yeah. And then we need to figure out one. Oh. Well, I mean, okay, that's just like no, but like if you look at which one's going faster? Blue one. No, I mean, well, red, orange, red, red. So, like, you know, the one and the higher one. So that one's going the first one is position. So that should be red. Yeah, orange is 2. Every second. And then blue should be 4. Yeah.
All right, let's discuss. So, all right. So, if you were paying attention before, I gave the answers away, or at least 2 of the 3. Okay. So, red car is represented by what line?
1.
Number 1 has the red dots on it. Blue car is represented by what line? Number 4. Okay? Number 4. Because number 3 would be a car that decides to do what? Speed up and go through the intersection, right? Okay? Okay? Then, orange car represent number 2. Okay? So, Taylor, I heard you explain it like well. How can we tell the difference between number 1 and number 2?
Because the red car has less distance before it gets to the light, so it has to slow down faster.
Right. That this car has to go, first off, right? First off, if we look at how fast they were going before they slammed on their brakes. Here's the red car, here's the orange car. Which one was going faster before they slammed on their brakes? Red was, okay? But because red was closer to the intersection, it had to slow down quicker, right? Meaning what about its acceleration?
It accelerates more.
It has a
Higher acceleration.
greater acceleration because its velocity changes more each second, right? Also, we can tell that from this graph by what? The slope on this graph tells us the acceleration. Okay? 1 has a big negative acceleration because it slows down really quickly. 2 has a negative acceleration, but it's not quite as great because he doesn't have to slow down as much and he has more time to slow down. Therefore, not as big of a change is required. But here's where it gets a little confusing. Because if we look at 4, right? What would we say about 4's velocity? No.
No, it's decreasing.
It's decreasing because it keeps getting closer to what, Julie? 0. But it's in which direction?
Negative.
4's velocity is in the negative direction. So it starts off low on this graph, but gets closer to 0. If we went to calculate its acceleration, however, by calculating the slope of that line, even though there are no numbers on it, what sign would it come up with? That has a positive slope, number 4, right? Meaning that its acceleration is positive. But physically, what is it doing? Slowing down. Okay? So we can't just blindly say that anytime acceleration is positive, an object speeds up, and every time acceleration is negative, it slows down. It depends on what's going on before that. Luckily for you, I have a chart that summarizes all of those possibilities, and it looks like this. Okay? So the top row, if we have a velocity that is positive, and then an acceleration that is positive, that means that the velocity is becoming more positive. Does that make sense? And if you start off with something that's already positive and make it more positive, you end up with a bigger positive number. And a bigger positive number means physically that object sped up. But in row 3, if you start with a negative velocity, and then you make the acceleration more positive, before it can go from being negative velocity to positive velocity, it has to pass through 0. So by taking something in negative and moving it towards the positive values, you're moving it closer to 0. And if you move it closer to 0, that means you're slowing down. Okay? So anytime that acceleration and velocity have the same sign, physically, that object is going to speed up. So it could be positive and positive, or it could be negative and negative. If you have a negative velocity, -4, and you change it negatively, right? A negative acceleration. If you go from -4 to -5, physically, what happened to that object? How does -5 compare to -4 from a velocity standpoint? Is it faster or slower? It's faster. It's just faster in the negative direction. So if you take negative velocity and make it more negative, that makes it go faster. Okay? But if you have an acceleration of 0, what does that mean? If the acceleration is 0, That means there's no what? No,
Acceleration.
I heard it.
Yeah.
There's no change. There's no change in velocity. So we end up with a constant velocity. Okay? Good there. All right. For this weekend, if you didn't write it down before, I would like you to try a couple of problems from the back of chapter 3. So the chapter 3 assessments, which is at the end of chapter 3, numbers 64, 65, 66, and 67. Those are all conceptual problems. 70, 72, and 75. Those are calculations, looking at some graphs, calculating some values, etc. Good there? All right. Have a good weekend, everybody. I will see you guys on Monday.